This presentation is about improving capacity in groundwater monitoring, modeling, and its impact in our case study areas in Pakistan. Our key results show that each province needs to develop a strategic approach to monitoring. For instance, Sindh Irrigation Department does not undertake any groundwater monitoring. In Balochistan, there is some monitoring of groundwater levels, and in Punjab they monitor groundwater levels and salinity during pre- and post-monsoon periods. So really what's required is a step change in monitoring, and the use of loggers has helped communities realize impacts such as declining groundwater levels and salinity. From a groundwater management perspective, our models have been used to estimate sustainable yields for LBDC and the left bank sucker barrage models. And these estimates are helping our stakeholders to develop improved understanding of the groundwater system. There's also growing realization amongst partners that groundwater management areas are required to improve management of groundwater. And we also found there are limited options for Kuchlak, where we need to reduce extractions and increase adaptation measures. Our main impact showed that some farming families have improved awareness of groundwater conditions, and that there is willingness to adapt, for example, by adopting low delta crops in Punjab and Balochistan, intercropping in Sindh, and drip systems in Balochistan. There is also greater awareness and willingness to use apps like Apna Pani and EC meters by our stakeholders. Our project partners have also developed improved understanding of groundwater conditions. We found the use of loggers has helped, and experience in model development has also happened. We are also evolving ideas for management strategies in case study sites, and there is understanding that improving groundwater management will require plans. We have also established networks, and there's greater trust and partnership between farmers in case study areas and researchers, and increased collaboration between academics and irrigation departments. To improve groundwater management, we recommend, firstly, strategic monitoring of the resource. This is going to help groundwater users and stakeholders to develop a better understanding of groundwater resource conditions. Establishing groundwater management areas is needed to ensure that groundwater depletion is managed within acceptable limits. Selective management of hotspots with community supports, and adaptive management strategies to allow increased extractions during drought. We also need continued knowledge and capacity development, particularly better understanding of groundwater at the basin level, and involving groundwater users who are empowered to co-design with government stakeholders a more sustainable future. And lastly, we need to rethink how groundwater is used and managed in Kuchlak, which is vital for sustaining agricultural livelihoods. In this respect, we propose a 3-decade planning horizon accompanied by phased long-term extraction thresholds and managed aquifer recharge. We also recommend future investment by ACIIR, donors, and the government of Pakistan to build on the approach developed in this project, preserving and making data from this project available to benefit future investments, and increased investment in capacity development. We also believe our team is well placed to provide reflective evaluation for future initiatives undertaken by irrigation departments. And in this last slide, I would like to leave you with a thought from Lord Byron's epic Don Juan. Till taught by pain, men really know not what good water's worth. And this epitomizes the evolution of water management in Pakistan. Next, we have 3 presentations which will cover groundwater modeling results in our case study areas. Thank you.
Water balance assessment for the model domain showed net declining trend. Major outflows include pumping from freshwater lens and evapotranspiration from groundwater table. Major inflows include irrigation return flows and leakage from major canals and river Indus. The net loss in storage over the simulation period was estimated to be 1.04 BCM per year, averaged over the simulation period. Based on the modeling results, the sustainable yield was estimated to be 3 plus minus 0.3 BCM, which will allow farmers to adapt during the times of drought and inadequate surface water supplies. Based on the modeling results, it is recommended that an allowance of 10%, which is 0.3 BCM, should be allowed for farmers so that they can increase extraction during drought years. This will have potential to replenish the aquifer when rainfall and surface water flows increases. All of the irrigation divisions in the model domain showed net declining trend. Khairpur East, Khairpur West, Rodi and that division showed major decline. In Nusrat division, the net decline was less as compared to other, making this division the only division where shallow water levels will prevail. Water level assessment in different scenarios showed that area near the Indus River will have declining trend. This will help to reduce the waterlogging in the area. One aspect should be kept in mind that as the groundwater will increase, the water quality will also deteriorate. We found out through resistivity survey in the study area that there is deep freshwater lengths up to 50 meters near Indus River, and its depth decreases as we move towards Rodi Canal. At the east of the Rodi Canal, the quality is not suitable for irrigation at shallow depths. As the pumping will increase, the lateral movement of the saline water will affect the quality of the freshwater lens. In Nusrat division, water table control is of prime importance to control the land degradation due to waterlogging and salinity. Major outflows in this region is due to the drainage network. When we simulated the long-term simulation without drains, the Nusrat division showed completely waterlogging. Based on the water level assessment, we can conclude that pumping should be allowed that of as present rate but with continuous monitoring. Drains should be properly managed for controlling agricultural land, especially in Nusrat division. Picture at the right shows farmer Zulfikar Darejo. He is helping us to set up an instrument in his field for the resistivity survey. One of the biggest impact we observed in the field was farmers' willingness to cooperate in the research activities and to take action based on the data generated during the research activity. We did this survey on the request of the farmer, where he intended to install a shallow tube well. He requested us to perform the survey so that he could install pump at suitable depth. Farmer not only used the survey results to install the tube well, but he also operated the tube well in conjunction with the surface water on rotational basis. EC meter provided in the project helped farmers to set optimum surface and groundwater ratios for conjunctive water use. Other farmer at the same site also installed filter plant in his house and in a positive tone told us that now his family is drinking safe water. This project also helped us to train Sindh irrigation and other line departments in advanced GIS and modeling tools for formulating plans for managing the groundwater in irrigated environment. This is essential because provincial department's main focus is surface water. Sindh irrigation department lacks in skilled staff which can assist and manage groundwater in a suitable manner. This project also helped in developing a multidisciplinary team of researchers which is dedicated in exploring options for sustaining aquifer and agricultural land in Sindh. Based on the findings in the project, researchers in the project also acquired fundings from other donors to extend the approach developed in the project. There are 3 domains, is that groundwater policy, groundwater legal framework and groundwater management, where interventions are needed in Sindh. So looking at groundwater policy, first step is to generate knowledge about quantity and quality of groundwater, to quantify the dependence on the groundwater, and quantify the economic value of the groundwater. Then the next step is to identify groundwater management areas and set groundwater use limits for sustainable management. In this project, we generated this information for the selected study area. Based on the field investigation and modeling results, we recommend that freshwater lands along the Indus River should be designated as groundwater management area for overexploitation with sustainable yields of 3 plus minus 0.3 BCM. Nasser division to be declared as groundwater management area for waterlogging and increasing salinity. Rehabilitation of scarp wells and maintenance of drainage network is recommended in Nasser division. Second step is to make rules to legalize the management and use of groundwater in Sindh. This is still a grey area and need further research for exploring feasible options for consumer and operators and setting up a legal framework for sustainable groundwater use. Third step is to build ownership, set up a groundwater management directorate, train irrigation officers to assess and manage groundwater resources in Sindh. Also establish stakeholder forums to sensitize the topic of sustainable groundwater management among the farmers. In this project, we trained line departments and established stakeholder forums as a pilot. But still there is a huge gap to fill for the future interventions and to sensitize the sustainable groundwater management issues in Sindh.
The key results for Punjab groundwater model can be seen from these arrows where the three major water budget components, average seepage losses from the rivers and the canal system are 1,556 MCM per year was recorded, total recharge 3164 MCM per year, and the dual extraction 4316 MCM per year. And these results show that groundwater extraction is higher than the recharge. However, the net gain in storage in the study area over the simulation period was observed as 87.9 MCM per year, indicating that there is very less potential or little potential for increasing groundwater extractions, and advisable that only extraction in the drought year. And for sustainable yield, for whole of the LBDC command area, 5% we can allow farmers to increase extraction only during the drought years. And for LBDC districts, Okada and Sahiwal, this is 37 MCM per year, and this is for Sahiwal, and these two sites can be designated as groundwater management zones that can be managed to ensure that groundwater depletion is managed within the acceptable limit. And here you can see that the total 7 scenarios were decided. The first 5 scenarios were suggested by PID, and the 2 climate change scenarios were modeled to understand the impacts by 2047 under changing climate, that is RCP 4.5 and RCP 8.5. So if we discuss this RCP, and the results can be seen from this figure, that how much change in storage would be takes place. So if we discuss this 7th scenario, RCP 8.5, with the current situation, that is S1, an estimated 179 MCM of additional water can be stored in the underlying aquifers of the LBDC, and also RCP 8.5 indicates that pumping could increase in response to increasing cropping intensity. And also this we can see from here that groundwater levels are likely to rise rapidly in response to high rainfall events in the study area. And for the impacts, I would like to invite Mr. Saleem to discuss these impacts of the study.
Ground modeling have following impacts. The main impacts on the aquifer management, and other is groundwater governance. So for aquifer management, the main impacts on the data. So we enhance the capacity of the local user as well as the researcher through stakeholder participation from academia, farmers, national and international. We also enhance the capacity through training, GS training, groundwater training, groundwater level monitoring, and how to take monitoring through different scientific instrument, data loggers, also surface water monitoring and water use in different sectors like domestic and industrial. So on these monitoring, we have got the main evidence-based data, which helpful the government for the developing of the policy and law on the decision making for future water use, groundwater use, like how can farmer get more water, where the new tube will be installed, and the metering and the licensing system. So these have main impacts on the groundwater modeling. On the other side, we are recommended the main purpose of groundwater modeling, the integrated resources management, and through optimized using of surface and groundwater in different sectors, agriculture, municipal, industrial, and to enhance our irrigation systems, surface irrigation systems. So it's also recommended, I have also recommended that the data results of these groundwater modeling and the LPDC should be shared at regional level, national level, as well as international level between the academia and the water user. So can we get more beneficial benefit from these results? We also requested at the national level that we have to implement the policy and law for sustainable water use through scientific instruments, scientific techniques, by giving the subsidy as well as the training to the farmers as a researcher. So we have recommended on three sides one is the water user, the second is the instruments, and the third is the institutional setups. So these are final recommendations. Thanks.
In the Kushlak sub-basin, observation bores exhibit declining water levels of between 30 meter to over 100 meter in a span of 8 years. It is a clear indication that unconstrained pumping is resulting in a race to the bottom. This is unlike anywhere in the Pakistan. We pose the question to policymakers and government of Balochistan, can it get more alarming than this? The water budget for the overall model domain from October 2010 till September 2018 shows recharge of 32.8 MCM, which is the main inflow to the groundwater system, and outflows are dominated by pumping from deeper layers at 427.3 MCM, followed by boundary flows at 56.65 MCM, which exit the sub-basin along the southern model boundary. The net loss in the groundwater storage over the simulation period is a staggering 451 MCM per year, which equates to an average decline in water levels of 5.4 meter per year for Kushlak. This, as many authors have indicated, is a race to bottom. In Surkhap Lora, groundwater depletion is 86 MCM per year, equivalent to an average decline in heads of 6 meter per year, which indicates a concentration of pumping. The groundwater depletion is minus 158 MCM per year, equivalent to an average decline of 6.2 meter per year in Rukhilora. Groundwater extraction comprises about 54% of the total pumping from Kushlak, making it almost heavily exploited watershed in Kushlak. The groundwater depletion is minus 109 MCM per year, equivalent to a decline of 3.9 meter per year in Saryap Lora. Groundwater is heavily exploited in this region also. The fundamental change we have observed over the project are willingness of all partners to listen to the needs of the irrigators, improve understanding of how water quantity is affecting farmer enterprises, The most beneficial change in community was support and engagement in monitoring water levels and water quality in the case study areas, which is creating awareness about the condition of the resources and need to change practices to ensure sustainable agriculture in the area. Willingness to adopt new cropping pattern and water management practices was seen and adopted during the project period. This picture, which you can see on right, is where farmers were given pomegranate seeds to be installed into the fields to adapt for low delta crops. There is no one solution for Kushlak. It requires number of different approaches. First of all, it is necessary to improve the monitoring system in the area. Then when monitoring is established, the longer term plans should be developed. Rethinking groundwater management strategies for Kushlak is critical for sustaining the livelihood in the area. Gradual reduction in the extraction limits over the 3 declared planning periods accompanied by adaptation measures should be employed. The RAPS approach need to be pursued by government of Balochistan agencies to introduce low delta crops and high value crops that will result in less demand on groundwater. Support from development banks may be possible for scaling RAPS in Pishin-Lora basin. Better use of flood water and runoff from mountain slopes include check dams, subsurface dams and other structures. This will require an integrated approach to surface and groundwater management to sustain livelihood in the area. Then the other step is the capacity development and financing for MAR options, managed aquifer recharge options. Capacity development for stakeholders, farmer community and groundwater users in improving water conservation practices is also required. Dedicated project that investigate various options for managed aquifer recharge, design of appropriate deep injection wells and other options to recharge the aquifer need necessary consideration.